For generations, the mountainous terrain of China's Guizhou province was a place people tried to leave. Today, if you look at those same slopes, you will see thousands of solar panels stretching for kilometers in every direction. Major tech corporations, including Apple, are setting up massive data centers right in the middle of this remote landscape. The electricity keeping those high-density servers running comes entirely from the sun and the wind. Look at this chart comparing global electricity generation over time. In 2025, the journal Science highlighted a major milestone. The line for solar, wind, and hydroelectric power definitively crossed above the line for coal. When we zoom out to look at daily capacity additions, the growth curve for renewables goes nearly vertical. We are now adding about 2 gigawatts of solar to the global grid every single day. That pace significantly exceeds the total growth in global electricity demand. For over a century, the logic of industrial growth was rigid. If you wanted to meet rising energy demand, you had to burn more fossil fuels. That structural equation is officially broken. If you look back at the early 2000s, building wind and solar in Europe and the United States relied heavily on government subsidies and tax incentives. Corporations invested because the state made the technology financially viable. But the International Renewable Energy Agency has tracked a critical shift in what is known as the levelized cost of energy. Levelized cost is a metric that accounts for every expense across a power plant's entire lifespan, from initial construction all the way through to decommissioning. On that basis, solar power is now strictly cheaper than burning fossil fuels. This holds true even with the gradual decline in global oil prices we have seen over recent years. The old assumption that cheap oil and gas would permanently stall renewable adoption has simply been overtaken by the data. The expansion of green energy is no longer fragile or dependent on public goodwill. It is expanding aggressively because it has a brutal, undeniable economic advantage. The central driver of this massive scale is China. The country now manufactures around 80% of the world's solar panels and 70% of its wind turbines and lithium-ion batteries, leaving the Western nations that invented these technologies trying to catch up. It is worth noting that China has not stopped building coal, oil, and gas plants. They are expanding conventional energy in parallel. The strategy is economic augmentation, using cheap, domestically generated electricity to lower manufacturing costs, substituting cheap energy for cheap labor as their domestic wages rise. You can see how economics outweigh political rhetoric by looking at the United States during Donald Trump's first term. Despite vocal support for fossil fuels, more coal plants closed during those 4 years than under his predecessor, while wind capacity hit record highs. Energy markets operate on massive, multi-year investment cycles that simply ignore political posturing. Here is a chart illustrating the mechanism driving these cost reductions, a principle known as Wright's law. It observes that every time production volume doubles, cost drops by 20%. While accessible fossil fuels eventually deplete and get more expensive, solar panels are complex engineered systems. Over the last 50 years, the cost of a single watt of solar capacity has plummeted from $100 to under 40 cents. By building massive factories, China accelerated the planet's accumulation of production volume. They pushed the global industry down that cost curve faster than anyone else. But this massive deployment introduces a serious engineering problem. Our legacy electrical grids were built around stable, continuously operating sources, like these massive coal and nuclear plants, not weather-dependent energy. The sheer volume of solar and wind generation has created negative electricity prices in Shandong province. Power companies actually have to pay consumers to use surplus energy during peak daylight hours just to prevent the grid from overloading and damaging equipment. This map of China highlights another major friction point. The country's most productive solar and wind resources are located in the sparsely populated west and north, thousands of kilometers away from the dense industrial demand centers in the south and east. To fix this, the state is spending hundreds of billions of dollars to modernize its transmission lines. They are also requiring renewable producers to co-invest in massive battery storage systems, a mandate now viable because battery prices have hit historic lows. The sheer volume of intermittent power flowing into the system has turned large-scale energy storage from an expensive luxury into an absolute requirement for survival. This new economic reality is accelerating energy adoption across the global south. Countries without their own fossil fuel reserves are buying into solar and wind out of pure necessity. bypassing the volatile global market for imported fuels. When rolling blackouts from failing coal fleets crippled South Africa, the country responded by rapidly installing distributed solar. And in Ethiopia, where severe droughts have repeatedly disrupted the hydroelectric dams powering their grid, the government is aggressively pivoting to alternative renewable sources. All of this is happening right as global electricity demand surges. Mass electrification of passenger cars and high-speed rail networks is replacing liquid fuels, putting demand directly onto the power grid, right alongside the enormous baseload requirements of modern AI data centers. Falling renewable costs and rising electricity demand are highly complementary forces. The surge in consumption provides a massive commercial incentive to quickly build out the absolute cheapest available generating capacity. If you look at standard charts of global primary energy consumption, you will usually see a picture that looks like this: massive bars for coal, oil, and natural gas, with renewables appearing as a tiny fraction down near 14%. So why the massive disconnect? The answer lies in the second law of thermodynamics, which dictates that no heat engine is perfectly efficient. When a coal plant burns fuel, it only converts about 1/3 of that thermal energy into actual electricity. The other 2/3 dissipate into the atmosphere as waste heat. Yet standard primary energy statistics count all of that wasted heat as energy consumed. Solar and wind power operate differently. They convert physics directly into electrical current without any intermediate thermal cycle. Because there is no steam and no wasted heat, a coal plant looks statistically 3 times larger on this chart than a solar farm that generates the exact same amount of electricity. Think of it like comparing an electric vehicle to a gas-powered car. If both drive 100 kilometers, primary energy accounting credits the gas car for all the fuel burned just heating up the engine block. It looks vastly more energetically significant on paper, even though it accomplished the exact same amount of useful work. The standard metric heavily penalizes efficiency. It creates a massive statistical illusion that makes inherently wasteful fossil fuels look far more critical to our modern energy needs than they actually are. In 2025, when the Energy Institute updated their methodology to stop overcrediting this waste heat, the reported global share of renewables instantly fell by half on paper. Absolutely nothing physically changed on the electrical grid. It was entirely a mathematical adjustment. To accurately measure this transition, you have to look at final energy consumption and direct electricity generation. By those metrics, the growth of clean technology is clear, rapidly accelerating, and showing no signs of slowing down. Look past the statistical illusions and the political rhetoric. The physical and economic realities confirm this industrial transformation is already structurally complete. We are no longer debating whether an energy transition will happen. We are simply waiting to see how the geopolitical and industrial consequences of this reality will unfold across the globe.